Hello, everyone. My name is Mahdi Azizian, and I'm pleased today to talk to you about the next generation intelligent surgical robots. Here's a brief overview of the agenda we're going to go through. First, we'll take a look at the state-of-the-art surgical robotic systems. How do they look like? And then we talk about the next generation of surgical robots, which we think will be data-centric architectures. And then we briefly touch on the pathway from development to deployment and what are the compute requirements for that and how to get from clinical decision-making to AI that is used in action. Then I'll pass it over to my colleague, Sean Hoover, who will talk about data and next-generation models with some of the announcements that you have seen already at NVIDIA. He will dive deep into those. And then we will basically go over agentic systems in smart hospitals, and then we'll summarize and wrap it up for some questions and answers. So if you look at the surgical robots of today, you can categorize them from a few different angles. One is by the access method to the human body. Obviously, open access robotics has been around for quite a long time in orthopedics, cranial, spine applications. Multi-port robotics in laparoscopy, thoracoscopy, arthroscopy have been around for the past 3 decades or so and in use. And single-port robots are a little bit more basically recent with the likes of Da Vinci SP and equivalents of those that are being used. And endoluminal robots, there's a wide range of things from nodes to endobranchial, endovascular, and different types. And incisionless robotics, the types of focal therapy, HIFU, histotripsy, and those. And each of these basically have different types of requirements. So mostly we're going to focus on the left side of the screen with multi-port, single-port-like systems. But the phenomena that we talk about applies to all of these, basically. You can also categorize by embodiments. So you can envision a surgical robot could be basically multiple arms on a single cart on wheels. This is probably one of the most popular types of systems that is out there. Many of these are manufactured by different medical device companies. Or it could be actually on multiple carts on wheels that actually get around an operating room table. It could be also mounted on the operating room table, like the Ottawa system from J&J, or there are different types that are basically bolted to the floor or to the ceiling, especially focal therapy robots have those type of embodiments a lot. The other categorization you can look into is actually from the levels of autonomy. This is actually from a paper in Nature by Ben Rappaport and team from a couple of years ago, where they have built on top of the seminal paper from Guangzhong Yang and team in Science Robotics in 2017, where they tried to define and get into a consensus on different levels of autonomy for surgical robotics. The green curve that you see over there shows basically how much of the existing robotic systems are in each category, and majority, as you can see, are in level 1, which is robots that assist you, mostly teleoperated robots. And obviously, there are few that are in level 2 and level 3 with task autonomy and conditional autonomy, but there are very few, and mostly they're in rigid body type applications. And there's pretty much nothing commercially available with level 4 or level 5 autonomy. But those, there's a lot of research groups and startups working on that, and those will be coming in future as well. And some of the architectures we're talking about is actually enabling not only the level 1 systems, but also enabling the higher level autonomy systems. So a typical surgical robotic system, a teleoperated one, has 1 or 2 surgeon consoles that the primary and secondary surgeon are sitting at there. That could be a trainee and a mentor, or basically 2 surgeons who are sharing responsibilities, or just a fellow who's actually watching the surgery. There's usually a vision tower that endoscope and all accessories are connected to, and a surgical robot. So this is a very simple architecture of what exists today. Often the modern surgical robotic systems have a connection to the cloud, a virtual private cloud that is used for over-the-air updates, maintenance, collecting data, and sometimes basically also kind of remotely connecting to the system and doing things like, for example, telementoring. And we see more and more of edge AI sidecars being added to these systems as an afterthought to bring AI capabilities to the edge of surgical robotics. If you look at a little bit more details of how different components of such a system are connected to, this is just a representation and an oversimplified way of talking about how different components of a surgical robot are connected to. There are many different components. This is by definition a distributed system. And each of those are connected with often proprietary type of connections to each other. So the surgeon console to the vision card, to the surgical robot itself, and the connection between different parts of that. Sometimes there are star configurations or daisy chains with different types of basically cables, signals, protocols. And this makes it extremely difficult to actually move from one generation of a robotic system to the next generation, because you basically have to maintain something that A to Z is proprietary, is not interoperable with other things, and often you deal with obsolescence of basically parts that are supporting that. So that's one of the reasons we're actually thinking that the next generation of surgical robots, like many other robots, are going to be data centers on wheels or data centers bolted to the operating room, depending on what embodiments that you're talking about. Data centers are very extensible. Let's take a look at a few parallels from different industries. If you look at the autonomous vehicle industry, especially in the Bay Area, you see a lot of startups who are working on AV. Some of them now are big companies that have products in the market. You probably have took a ride with Waymo here. That you have seen how it works, but often if you have the inner guts of a prototype, it's actually that ugly. You know, this is a trunk of a self-driving car under development. You see very different types of cables, different protocols, and different connections. Extremely difficult to maintain and deal with multiple different vendors and complexities that comes with that. And here is actually a view of a data-centric autonomous vehicle. So you can see actually that the ECUs, or the brain of the car itself, is basically connected over Ethernet to pretty much all the sensors and actuators in the car. And that enables you to easily expand. If you want to go from one generation to the next generation, add more sensors, upgrade your sensors, change your actuators, increase the capacity of compute. This is simply a data center. You just change the compute, you change the sensors and actuators, and everything stays the same. It's all Ethernet based. It's interoperable. Makes you capable of actually working with different vendors and even have basically a system that is built by multiple different companies. Same goes with humanoids. If you look at legacy humanoids, it's actually kind of funny to call humanoids legacy. They're newer by definition, but what is in the market has been following what has existed in kind of robotic manipulators and also AV. So often there's fixed input and output that limits basically the sensor count that you have. You can't easily add more sensors. You have separate buses for sensing and actuation, and then you basically end up with something complex and expensive to deal with. You have limited safety and fault tolerance, and there's heavy usage of CPU for handling the traffic, versus a data-centric humanoid design that we're basically working on with some of our partners is all Ethernet based. Again, you have a brain of the humanoid, that green box in the chest of the humanoid, that has flexible I/O over Ethernet. So you're only limited by the bandwidth of the Ethernet links that you put in there. You have a unified network for sensing and actuation. Everything is synchronized on the same network. This drastically reduces the complexity and makes it more fault tolerant, and also because of the network acceleration that these basically brains of systems bring in that we'll talk about, it offloads the CPU usage. So you basically have direct access in and out of GPU memory. So here's actually a view of that, a very simplified view of what a data-centric surgical robot would look like. You can actually see in the bottom that you can have different edge computes for different zones of a surgical robot, for lack of a better word. You have a simulation zone, surgical console zone, a robotic zone, endoscopy zone, and accessories zone. You have a backbone of basically an Ethernet network, and you can have a redundant backbone as well for safety purposes. And pretty much all the input-output in the system is dealt with Ethernet. Holoscan sensor bridge that we briefly touch upon after this enables you to pretty much convert any type of signal in and out of Ethernet and basically make that RDMA-able. RDMA stands for Remote Direct Memory Access to GPU memories. So we'll double down on that a little bit. So let's get a bit geeky here for those of you from MedTech. If we want to look at the highest level of requirements for a data-centric robotic system, you want the robotic network to be end-to-end Ethernet-based. And you want to have the data accessible in real time anywhere within the system, so you don't have to redesign things to get, for example, the endoscopic image on the other node or this joint encoders basically in another node. Everything should be accessible everywhere with software configuration. Ingress data from sensors should be accessible in any processing unit with minimal latency and jitter. That's basically a requirement, and vice versa. Egress data from a processing unit should be accessible to controller units, whether it's a motor controller or display controller, again, with minimal latency and jitter. There shall be redundant access passes, obviously, for safety-critical data, and all of ingress-egress data should be synchronized, obviously. You want to have data authenticity and security. That's an obvious requirement because you don't want someone to connect with their laptop to the system and try to hack into that. And switching, this one is probably one of the most important features that this enables, that switching between a digital and physical twin of a robot becomes seamless with this type of architecture. With the change of IP address and port, you'll be able to actually switch from a digital version of a sensor to its physical version. So development cycles become much faster because of that. You don't need to create hardware abstraction layers and basically make ad hoc simulation bridges. The processing units obviously shall be able to record data and play back that data seamlessly with synchronization and consistency. So let's take a closer look into performance. I'll just give you a very simplified example of that. Imagine that you want to talk about event-to-action performance on a surgical robot, which is the core of what it does. You know, a teleoperated robot is detecting something, you take an action based on that and go through. So if you have a chip-of-tip sensor, imagine an endoscope, in a regular surgical robotic system, you have it go through an ISP, an image signal processing pipeline, going through a video router, through a frame grabber, often on a different physical node, to a processing unit, doing some processing on that, and then to a controller unit, and then back to a motor controller to a robotic arm to do something. And I'm not showing surgeon in loop here just to be able to talk solid about the performance that you get. The best things that you find in the market for this is like 50 millisecond latency from basically the start to the end in terms of what performance that you get. The data-centric version of this will be something like this, that you have the chip-of-tip sensor, the raw data over, say, CSI MIPI, goes through Holoscan sensor bridge, directly written to GPU memory. So as the lines are being scanned in your camera, they're basically written in GPU memory. In another word, the GPU memory becomes extension of your sensor memory. And then it goes to a Holoscan SDK pipeline on the GPU, which is basically a graph for processing. And then you can basically go back out over Ethernet to a microcontroller that is controlling your robotic arm. And benchmarks on this that we have done shows a speed of light implementation of 1.2 milliseconds from the input to the output. So you see the difference that you get going from 50 to 1.2 milliseconds on this. How is this enabled? We have a smaller version of our data centers on the edge for these type of robotics deployments. This is the high-end version of that, called IGX Tor T7000. There are different versions of it with basically different levels of compute and price points, obviously. This one brings over 5,000 teraflops of FE4 for inference, and you have the option of adding an RTX Pro 6000 if you need more compute. You get 128 gigabytes of memory, and more importantly, you basically get up to 400 gigabit per second of Ethernet bandwidth to this, which is twice of the previous generation, which was IGX Orin 700. And then next generation, it'll be doubled again. It'll go to 800 gigabit per second. So without doing anything, this data-centric approach will give you future-proofness. The I/O part is enabled by Holoscan Sensor Bridge. This is a very simplified reference design of that. It is an FPGA IP that we have made public and freely available for everyone who wants to put it in their FPGA. It's pretty much supported by any FPGA vendor. There are many of our partners who are building ASICs out of that, and also it comes with a software emulator that you can run it on a microcontroller or on any CPU, basically. So you can convert pretty much any type of signal that you get from I2C, SPI, and GPIO to JSD, MIPI, CSI, LVDS, and so. And on the other side, you will have Ethernet in and out, time synchronized if you have multiple of these, and directly accessing GPU memory. This is enabled by NVIDIA networking acceleration provided with ConnectX. So this is the 1.2 millisecond pipeline that I was talking about. If you look at the top left, you see the stereo camera connected to a Holoscan sensor bridge implemented on this is a Lattice FPGA. It goes over an Ethernet link to an IGX and gets processed in a Holoscan pipeline. What you see on the right side of the screen, the green is a laser pointer controlled by a human, and then the red is basically what that Galvo laser pointer at a 2 degree of freedom robot is basically shining on the wall to track the. Let me try to play it again if possible. To track basically the green. And you can see that it's almost perfectly tracking that. The little offset is because of calibration. So that 1.2 millisecond is getting into basically from shutter close to the GPIO command sending to the MCU. And the photon to photon here is 10 milliseconds, which is mainly driven by the time that the camera shutter basically needs to be open. If you look at this, obviously in a regular tele-operated robot, this can be used, but also you hear a lot about telesurgery because robots and surgeons are both scarce, and surgeons are more scarce, and you want to have the surgeons be able to operate in remote locations. So this is a very simplified kind of diagram of showing how state-of-the-art telesurgery works. Basically, on the patient side, you have the endoscope being processed and compressed, sent over the network, displayed to the surgeon taking an action. That action goes again over the network back to the other side, and the robot follows that. How this can be accelerated using this type of data-centric technology is that you can actually apply Holoscan sensor bridge and the NVIDIA acceleration to basically shove off latency on both the patient side and the surgeon side, because there's not much that we can do about network. You can obviously work with the likes of Sovato and other telesurgery companies and telecom companies to get the best network possible, but speed of light is limited based on the distance that you have. What we can do is shove off latency on basically the proximal and distal side of the pipeline and give a better performance and better safety to the surgeon who's operating. Let's quickly touch on the development workflow and how we are actually thinking about that. We see this type of problems, especially as you go to the higher levels of autonomy, as a three-computer solution problem. What it means is basically, if you're bringing AI to the loop, you need to train that AI algorithm. Often you need to actually involve some sort of a simulation, and then at the end of the day, you need to deploy it. But this is actually a cycle that keeps going on during your product development and after the product launch as well. So you may want to make sure that this cycle is very fluid and you have a flywheel running over there. This data-centric approach enables you to seamlessly, as I mentioned, switch between simulation and real world. So regardless of if you do it on-prem or on cloud, you will be able to use the same brain of the robot, say, based on that IGX, working with a simulation environment without knowing that is simulated and not real. Sean is going to talk about basically a modern approach to surgical simulation next after this. And you can actually envision that once you have this ready for deployment, you can implement it with a distributed compute for layered intelligence. Having the embedded intelligence in the robots, whether they're surgical robots or cobots, in the operating rooms, also having the signals from the room, like room cameras, on-prem compute in the hospitals, and cloud compute. And this will enable you to actually scale the intelligence as needed for your systems. Clinical decision support has been the main focus for many years with AI development for surgery. The likes of Cosmo AMD Genius platform or Medtronic Digital Surgery One have been adding edge compute as a sidecar to medical devices and then displaying the results of, for example, detecting a polyp in colonoscopy to the surgeon to help them with the clinical decision. But you can actually envision that AI can be used in action, closing the loop. This is Moon Surgical's co-pilot, where tracking of these instruments results in detecting of where the surgeon wants to look at and then autonomously moving the endoscope to basically help them locate that. With that, I'm going to pass it to my colleague, Sean, to talk about the data and the next generation models.
Thank you, Madi. So if you attended Kimberly's keynote on Monday, you've probably seen kind of the high level of this, but we'll be talking about the data that we released this week and how that's helping to fuel the next generation of AI models. So if you look at data available to train different types of generative models, if you scrape the entire internet, there's roughly 1 billion hours of kind of human existence for training data across math, across science, philosophy, medicine, etc. Now, if you look at what's available for general robotics, then that drops down to on the order of tens of thousands of hours. So this is why frontier labs in the general robotics space pay people to come in off the street and teleoperate robots for training data, such as folding T-shirts, doing the dishes, etc. Now, of course, when you look at what's openly available for healthcare robotics, this is especially dire. If you're a researcher, if you're a PhD student, and you happen to be at a university that does not have a DVRK, you're kind of out of luck. There's only 3.5 hours of open source data. This is a 10-year-old data set. It's still an amazing data set put out by Johns Hopkins called the Jigsaw's data set. So when we were looking at what we could do roughly a year ago in this space, then we decided to reach out to some of the luminary figures in healthcare robotics, folks such as Axel Krieger at JHU, Nasir Nawab at TUM, and we decided to build a coalition that we call OpenH Embodiment, this community-driven effort. And I think kind of beyond our wildest dreams, we grew from this initial group of 3 organizations to 35 partners, spanning industry, academia, as well as healthcare partners. Filippo Filicori, for instance, here in the audience, and his team of surgical residents helping to do annotations. So really, this great group came together. It actually became, I think, an easy sell to get people involved. And so the data set itself has 8 different robotic embodiments represented, all sorts of different data, spanning from simulation to tabletop to ex vivo animal to even clinical. So CMR Surgical made an incredibly generous donation of almost 500 hours of clinical data. So robotics, kinematics paired with video. So this data set went live on Hugging Face. I just checked right before this morning. Already over 1,000 downloads of a 4 terabyte data set in just a few days. So now that we have this great data set to work with, what are some of the things that we can do? One of the first models that we experimented with building is a vision language action model, a VLA. So NVIDIA has a series of models called GR00T for general humanoid robotics. So we took, building on that foundation, we then trained on all of the OpenH data to see what it could do in the lab with our partners, such as Johns Hopkins. So this is, being 2026 and AI moving as quickly as it is, I'm going to refer to this type of VLA architecture as a classical VLA, meaning that it's built upon a vision language model at its base, a VLM, if you look in the bottom left-hand corner. And this is what we saw when we pre-trained on all of the OpenH data and then did a little bit of post-training on suture data from an effort from JHU called SutureBot. So hopefully this will play. There we go. So this is running on a DVRK example, and this is an end-to-end suturing. So the model itself probably won't do great 0 shot straight out of the box, but it's been pre-trained on all of these different embodiments, on all of these different tasks, that it requires less data than you would need otherwise. So this is a good example. The pre-trained model is then post-trained on just a little bit of the suturing data. And what you see here is a successful example. And of course, full disclosure, there were many unsuccessful examples. We're quantifying the entire performance right now as part of an upcoming paper. So before I referred to this VLA as a classical VLA because this is it's almost out of date. We just published this model, and here's an example of what we're looking at in the future. Now VLAs, rather than having the vision language model as their backbone, have world foundation models as their backbone. So if you're not familiar, a world foundation model is a generative AI model that can generate video going into the future. So not only is this model from Semaphore Surgical, which is a company founded by Axel Krieger and some other JHU collaborators, so not only is it generating the kinematics of what the robot should do in the future, it's also generating the video. And some early papers are showing that these types of models, this type of architecture, is actually doing better than what we were seeing with the classical VLA. So now I'm going to switch gears a little bit and talk about, rather than a VLA, what world foundation models can do as far as simulating surgical robots. So this is our second model that we also open sourced this week, and it's called Cosmos H Surgical Simulator. So when world foundation models first appeared, they were typically text-driven. You would write a description of what you want. You may have seen this from OpenAI Sora, and it would generate a video a video based on your description. So this is different in that it's driven by the kinematics of the robot. So you give it a ground truth single frame image, and then the kinematics of your robot, and it actually generates each successive frame. So this model has been trained on all of the data from OpenH. So it's a single model that can do 8 different embodiment simulations across the different tasks that it was trained on. What you're looking at is suturing. And one thing I want you to take notice of here is, again, we're just giving it the first frame, and it can actually keep temporal coherence with how the ground truth evolved over a few seconds, and that'll be important for what I talk about a little bit later. So again, here's kind of an example of all different types of scenarios. These are all holdout test sets of what this model can simulate. Where we're taking this type of model next is these models are getting closer and closer to being real time. Currently, you might need to spend 10 minutes to generate a 30-second clip. But we can distill these models, make them smaller, and make them much faster. So our fastest version that runs on a single GPU today runs at about 12 frames per second on an RTX Pro 6000. But if you've been out on the show floor, there's a really cool demo for a driving simulator inside of Cosmos. And so if you've seen that, that's actually running at almost 30 frames per second, although full disclosure, that's running on 12 Vera Rubin GPUs. So it's a lot of expensive firepower to run that. But of course, this entire field is accelerating so quickly that we're reasonably confident that we'll be able to have a real-time version within the next 6 months. And once we have a real-time version, you can actually teleoperate these. So just like that driving simulator has a gas pedal and a steering wheel where you can interact with the World Foundation model, we'll be able to connect Hapley devices, for instance, and treat this as a surgical simulator. So, switching gears again, our third type of model, and this was just actually released this morning, is the tokenizer for real-time surgery. Telesurgery. So as many of you are familiar, in telesurgery, the surgeon controlling the robot, you use a classical encoder to encode the video to try and make the video packets as small as possible, reduce latency. So just like tokenizers are used for large language models, when you type a request, a text tokenizer turns your request into tokens where it lives in a latent space that the AI model understands. We now have the same thing for video, for telesurgery. So this has been trained on surgical video data, and these models are getting really great at high compression and high quality. This is changing very, very quickly. So this is an example of the model that we open sourced and put on Hugging Face, was made public this morning. We're really interested to see what types of experiments people do with this. And this is actually rivaling JPEG compression in terms of quality here. So if we put some of these technologies that I just talked about together, I'm going to describe real quickly kind of this idealistic moonshot experiment that we're hoping to do. So having these neural tokenizers means that we can put not just video data, but in the future, all types of multimodal data, whether it's audio, whether it's the kinematics, that all live in the same latent space that generative AI models can understand. And so if we feed those tokens into the World Foundation model that I described earlier, as that gets to be real time and that temporal coherence is good enough that we saw earlier, we might be able to predict what happens a few frames into the second. And so this moonshot experiment that we're hoping to do later this year is to see, can we shave latency off of telesurgery using these technologies together? So again, it's very aspirational, but this is kind of where we're headed in some of our ideas. All right, and I'll switch it, give it back over to Madi for the next section.
Thank you, Sean. Thank you, Sean. So I'm going to spend a few minutes to talk about agentic systems in smart hospitals, how to connect all of this intelligence that your system would architecturally support, and the models that Sean talked about would actually bring it on the edge. In 2024 at GTC, just 2 years ago, we actually showed surgical agentic copilot here. It was mainly, think of it as a chatbot for the surgeon and the operating room staff, bringing all of the EHR and PACS data, the surgical endoscopy feed live basically into a VLM, and also loading a RAG of the medical device documentation, and allowing basically the model to understand what is happening in the surgery and providing answers to any questions that people have. For example, what phase of surgery you're in, what instruments you're going to need in the next phase, and what complications the patient might face. This year, actually, we have expanded and built on top of that work and brought physical agents to basically this framework. If you look at the problems in that we have in the hospitals, a lot of that is around workflow efficiency. Just a very brief overview. Every minute in operating room in US costs around $46, and there are over 50,000 operating rooms. Just do the math. Surgical suites represent 60% or more of the hospital revenue, and there's shortage of 15 million healthcare workers globally by 2030, which is a major shortage. And the global surgical volume is expected to rise by 50% in the next 9 years. So if you put all of this together, any technology that you can bring in to actually make operating rooms more efficient is going to be extremely valuable, both economically and also from a patient outcome and society point of view. So the Rio workflow is a blueprint for hospital automation that we have published as part of ISAC for Healthcare 0.5, and a physical demo of that is at the Peritos booth on the exhibit floor. If you have not seen it, I would suggest to go and take a look at that. We start with the digital twin of a hospital. We train these robots to be able to do chores and be connected to these agentic frameworks. You can envision, for example, a robot that can go between the operating room and the sterilization processing department, SPD, to bring a tray back with instruments that are needed for the next phase of the surgery. In order to do that, obviously, you need a simulation environment. That's what ISAC for Healthcare provides. And this enables you, with combination of generative AI with Cosmos Transfer, to have synthetic data generation with thousands, if not millions, of different types of scenarios that you can use for training of the robot. And let's take a quick look at this basically blueprint in action. This is a Peritos robot that is trained to be connected to this agentic framework, which, for example, is monitoring what is happening inside the operating room in the surgery, knowing what phase you're in and what is the next phase, what instruments and accessories are required, and also checking the room camera to see if those instruments and accessories are on the table and available to the surgeon and staff. If it's not there, it will autonomously send over a message to the fleet of robots to basically go get it from the SPD department. It basically knows where to find it, goes and gets that and brings it over to the operating room. And it can get into more detailed type of actions of, for example, opening the tray and recognizing what instrument it is in there and putting it on the sterile table for the surgeon. Obviously, this is representative and requires much more productization work to be available at scale. But you can envision that once you have this fleet of physical agents in the hospital, they can do a lot of chores for you that are technically not medical device functionality, but it would help with the workflow in general. To summarize, we discussed the anatomy of existing surgical robots, the new way of data-centric approach. We talked about data and next-generation models and agentic systems in hospitals. A few points as food for thought. We think that future of surgical robotics will have data-centric architecture. We think that they will use raw data and tokens for data exchange rather than all different weird formats of things that exist today. And then we think they will be part of an agentic framework within the clinics. In terms of regulatory considerations, we're seeing signs that there will be pre-cleared foundational models that will help you with easily or basically with an easier flow to get clearance on a fine-tuning of that already cleared foundation model. And then that enables potential for subsystem clearances, which is super important. It enables new business opportunities by bringing interoperability, multi-vendor systems, and continuous feature rollout, and also starts changing the mentality of medical device companies to become software-defined, enables SAMD or software as medical device marketplaces, and potentially opens the road for general purpose compute platform where the regulation burden is going to be less. A few links that I would suggest you watch for if you're interested in this. This is NVIDIA Holoscan platform, which all of what we talked about is built on top of. The NVIDIA ISEC for healthcare, which a lot of these workflows going from simulation training to deployment are basically being shared and open sourced over there. And the NVIDIA MedTech, where you will find all these foundational models and links to the data sets for different efforts that we're doing in collaboration with our partners. With that, if you have more questions, we have a few minutes left. And if not, we can find time after or email us. Thank you. Sure.
Thank you, Madi and Sean. And yeah, if you have any questions, please come up to one of the microphones that are in the aisles. We have about 2 minutes. And if not, you can also speak with them afterward out in the hall as well. But any questions from, come up to the microphone here.
Thank you for the presentation. My name is Onur from LEM Surgical. You are using mainly Holoscan sensor bridge for connecting the physical world to the GPU. And for the medical devices, you're using IGX platform for the functional safety. Do you have plans to also embed the functional safety in the sensor bridge, also to allow AGX platform also to be used in the surgical platforms?
That's a great question. So Holoscan Sensor Bridge is an IP. So we have customers who actually have put that into their FPGAs and have added their own logic. Like, for example, they have added a soft core that they basically implement their logic inside the FPGA alongside of that. So it's completely configurable. For us, basically, we are adding some safety features, for example, watermarking, CRC checking, and certain things that we need to get a SIL 2 IEC 61508 level certification for HSP. That's something we're looking into. But the broader safety solution will come from the medical device manufacturer because it's specific to your own solution. But it is configurable, and everything, including the RTL for the IP itself, is all open source. So you'll be able to use it towards your design. Thank you.
I think that might have been all the time we have for questions. We're about to run out of time now, but if you have any other questions, you can follow up with them outside in the hall. But thank you, Madi and Sean, for the talk. Please give them another hand.
Thank you. Thank you.